Once again, welcome to this NPTEL video course on Advanced PDE Part 2. So far you have heard essentially the elliptic PDE portion, variational formulation, abstract formulation and other aspects. So now we will move on to study evolution equations. So essentially we will be covering the three important equations, namely the heat equation, which is a prototype of parabolic equations. In fact, whatever we study, you can apply even to general parabolic equations, and then wave equation, prototype of hyperbolic equation, and the one coming from quantum mechanics, namely the Schrodinger equation. So actually you do not have a classification for this equation, but because of its importance describing the dynamics of a quantum particle, so we have included this, and this falls in the category of evolution equations. So it is indeed possible, especially for the first two equations, heat equation and wave equation, one can formulate like you have seen in the case of elliptic equations, one can formulate these equations as a weak formulation and do a parallel study as you did it for the elliptic equation. But here we have chosen a different path for the study of these equations, namely we use the theory of semigroups of operators to tackle these evolution equations. And this semigroup theory has certainly played in unifying many of the PDEs, but nowadays it also plays an important role in other branches of mathematics, for example in control theory, probability, etc. Okay, so and there is also some nonlinear version of this semigroup theory, so we can also tackle nonlinear equations. So this is an important branch of mathematics itself. So we thought of giving some brief discussion about semigroup theory. Of course, we cannot do the theory in entire details, because that will take up the entire time for this course. Okay, so and to study semigroup theory, we do need again the study of unbounded operators from functional analysis. So these are the prerequisites. So you should study yourself and have some good working knowledge about these things. So I will just briefly recall some of the important things we will be using as far as semigroup theory is concerned. So after developing basic definitions and some results, we will just only state the important theorem, namely the Hill-Yoshida theorem, and then once after developing that semigroup theory and Helios-Shida theorem, we will come back to this evolution equations. So, as a motivation to study of this semigroup theory itself, okay, consider this ODE in a finite dimensional space, namely Rn. Okay, so du by dt is AU. So, A is an n by n matrix, real or complex, it does not matter. Okay. And for this Cauchy problem, so if you impose an initial condition, so this is in Rn. Okay. So, we know that the solution immediately given by e to the Ta u0. So, in fact, this one you can define for all t. Okay. So, in fact, we can consider such an equation in a Banach space. Okay. So, again an abstract Cauchy problem, Banach space X. Again you consider this ODE. Okay. Now, A is a bounded linear operator. Okay. So, this is space of bounded linear operators from x to x. So, that is my notation. So, we will be using again. So, you impose this initial condition. So, this is the abstract Cauchy problem. So, as long as A is a bounded linear operator, the same formula again holds. So, there is absolutely no problem in defining the exponential of a bounded linear transform. So, then we get more ambitious and then we ask what if we remove that boundedness. Okay. What if A is not in Bx? So, again we consider the abstract Cauchy problem, but now A is may not be even defined on entire X. So, it may be just a subspace. So, we call it domain of definition into X, linear. Okay. So, that is the setup. So, can we imitate the finite dimensional case and bounded case in order to again write this u t as e to the T A. So, I put this in quotes because we do not know what that is. Okay. So, is this possible? That is the question. And if yes, what is this meaning? What is this? That is the what is this? Okay. So, these questions are answered by the semigroup theory, and semigroup theory also puts necessary and sufficient conditions on such a operator. Now it is only a linear operator, there is no boundedness. Okay. So, let me just consider the heat equation and see how that can be put in this abstract formulation. Okay. So, typically evolution PDE, so like heat equation and wave equation, can be put in the form of an abstract ODE in some space. Okay. So, that is that x we have to. So, for example, so if you consider this du by dt, the heat equation. Okay. So, u is a function of x and t. Okay. So, what we do is, so we consider this as a function of u t belonging to some function space. So, for each t, so u of t is a function. So, u of t, so again this a temporary notation. So, for each fixed t, we consider u t as a function, not just a value, okay, because it also varies with x. Okay. With this understanding, so we can write this as, so du by dt as au. So, now au is the Laplacian. Okay. So, this a acts on a function space, and as long as we can give appropriate meaning and again class of u for which this is well defined. So, we can write this heat equation in the form of an abstract ODE. Okay. So, similarly we can do that for the wave equation and Schrodinger equation. So, once we study this abstract Cauchy problem, so we can apply those results to the wave equation, heat equation and Schrodinger equation. So, that is the idea, that is the idea. So, typically an evolution PDE can be written as an abstract ODE in some function space. Okay. So, x will be that Banach space will be some function space in each of these cases, and so we have to develop. So, what sort of operators A will generate the so called semi group or group. Okay. So, before we go further, so let me again just so for bounded matrices or for bounded operators, so we know this e to the T A. Okay. So, let me just put that as T of T. Okay. So, when A is a matrix or A is a bounded. So, let us recall some properties here. Okay. So, this T of T1 plus T2 is T of T1, T of T2, this is of course. So, they commute and this is again trivial thing, and with some simple computation you also see that this T of T minus I tends to 0 as t tends to 0. So, this one is either matrix or operator norm, okay, as the case may be. Okay. So, this is referred to as semi group property. In this case, it is also a group property because it is defined for all t in R here. Group property. And this is of course at 0 it is identity, and this is referred to as continuity. Okay. So, when we develop a general theory of such operators, so this each T is also in, let me write as Bx. Okay. So, this is what so this may not be defined for all t in R, but at least we hope for example, in the case of heat equation we can expect the solution only for t non-negative. Okay. So, at least we hope this one for t non-negative. So, that is fine. So, then it becomes only a semi group, not a group. And again this one, it turns out that is a very strong property. Generally not this, if this condition holds, then we get back to this situation. Okay. So, actually it turns out that suppose this is after much study. Okay. So, it is not immediate. Okay. Turns out that 3 implies T t is actually e to the t for a some bounded operator. Okay. So, since we are trying to develop the theory for unbounded operators, okay, so certainly 3 cannot be expected because otherwise if 3 is expected, then we again come back to the bounded case. Okay. So, this 3 has to be replaced by a weaker condition. 3 needs to be replaced. Actually, this is uniform continuity because we are taking in the norm. So, this is uniform continuity. So, only by strong continuity. Okay. I will define later okay. So, this is t of t x minus x tends to 0 as t tends to 0 for all x in x. Okay. So, this is strong continuity. Of course, one can even take weak continuity, but we will just restrict in all our cases the strong continuity is satisfied and we will stick to this. Okay. So, one of the important objects associated, I will define this semi group properly little later. So, we call it a semi group of bounded linear operators, or simply C0 semi group, we call it semi group, that is all. So one of the so Tt, so is a semigroup. So again, considering this e to the Ta, okay, so you can just see that e to the Ta minus I divided by T, this converges to E when A is a bounded linear operator. Okay, so this convergence is in the operator norm. So similar to this, we can now introduce this. Okay, so consider x belongs to x such that limit Ttx minus x divided by T as T tends to 0 plus exists. So this is in the norm of so whenever that limit exists, so you define A by Ax is limit so whenever this limit exists. So at this stage, it is not even clear whether there are non-zero x for which this limit exists. Certainly 0 is there. So, but so it's certainly defined. So this the set of all such x, the set of all such x in x, this is clear, forms a subspace of x and A is linear. So these are clear. Okay, so there is no problem with this. Okay. So in general, obviously we cannot expect this limit to exist for all x in x. Okay, so it will be only a proper subspace of x on which this A is defined. Okay, so A is, so call it this A from dA to x. So this is a subspace, and this is again in x, linear. Okay, so we call such linear operators as unbounded operators, since they are not defined on the whole space x. Okay, so this leads us to the study of these unbounded operators, and in order to get more properties of, so A is by the way called generator of or infinite generator. Of Tt. So we need to study in some detail about these unbounded operators. So of course I will not be able to cover that topic in detail. A good reference for these unbounded operators is again Rudin's functional analysis book, or whatever functional analysis book you have studied in which the theory of unbounded operators is covered. So, this also contains a brief discussion about semigroups. So, you can also see that. Okay, so, this is one you can keep in mind. Okay, so, the importance that A is not defined on the whole of X is given in this theorem. In fact, this is very old theorem of Hellinger-Toeplitz. This is somewhere in, it's more than 100 years old. So, somewhere in 1910. So, let H be a Hilbert space and so T from H to H be linear and symmetric. So, that is Txy is equal to Xty for all xy in H. Then T is bounded. So, it is important here that T is defined on the entire space. Okay. Later on we see symmetric operators which are not defined on the entire space, they need not be bounded. Okay. So, this is an easy application of closed graph theorem, and there are extensions also. Okay. So, that is so this when we replace this H by a proper subspace, there are many interesting things happen and we move out of this bounded regime. Okay. So, let me okay. So, let me just with that motivation, so we can now a quick review of unbounded operators. Okay, let me just begin and I will continue in the next class. So, X is a Banach space. Okay, so for our discussion. So, with norm, right. So, A is from some subspace. Okay, so is linear. Okay, so this dA again important thing. So, it is the domain of definition of A. So, soon we will see two operators can have the same expression, but with different domains of definition, and they are certainly different. Okay. Okay. So, we introduce this so called graph norm of A Ax. Of course, since we are using Ax here, so this is defined only for dA. So, you can check that with this graph norm, this space dA, subspace dA becomes a norm linear space. I will stop here and continue in the next class this discussion. Thank you.